We're going to take a look at a new term in this video. We're going to take a look at something called inscribed angles. So let's first come up with a quick definition for what an inscribed angle is. You can see one down here. It says angle C is inscribed in circle Q. And if you notice what's special about angle C, there's a couple things. First of all, you look at where its vertex is. Its vertex is on the circle. We had talked previously about central angles, where the vertex was at the center of the angle. For an inscribed angle, it has a vertex on the circle. So an angle whose vertex is on a circle. And then if you look at the sides of this angle, they're both chords of the circle. So we say an angle whose vertex is on a circle and whose sides are chords of the circle. Chords of the circle. So what we're going to first take a look at is what the relationship would be between an inscribed angle and the arc that it intercepts. So you can see angle C, or angle ACB, is our inscribed angle, and it's intercepting this arc right here, right? It's intercepting arc AB right here. And so the question I want to take a look at is, what is the relationship between the measure of this arc and the measure of angle ACB, right? So let's just kind of reason our way through this. Now in this picture, we've also, you'll see, we don't just have that inscribed angle. We've also drawn a radius that goes from Q out to B, right? So the end points of the arc intercepted by my inscribed angle are A and B. Those are the end points of my arc. And I have a radius that's drawn out to each one. Now I've decided that this central angle right here, the central angle that's also intercepting this arc, has a measure of x degrees. So that would tell us then that arc AB also has a measure of x degrees. Well, if that's true, let's think about what the measure of angle C would be right here, angle ACB. I'm going to look at triangle QCB. Now, like it says here, it is isosceles, and the way I would know that it's isosceles is because two of its sides are radii of this circle. So segment QB is a radius and segment QC is a radius. And I know that they would be congruent. Now, technically, this one would be congruent as well, but that one I'm not as concerned about. These two are congruent. And so that means that this angle and this angle would be congruent. So I'm going to just establish that fact over here. I'm going to say that the measure of angle ACB will be equal to the measure of angle QBC, right? But then if I look at this triangle and I look at this angle, this is an exterior angle for this triangle. And we've learned previously that the measure of any exterior angle would be the sum of the remote interior angles. And that would be these two guys here, those base angles of my isosceles triangle. So I'm going to state over here that if I took the measure of angle ACB and I added it to the measure of angle QBC, I should get x, or x degrees. These two added together should equal this x, which of course, remember, is also the measure of arc AB. But now if I take out this QBC right here and I replace it with angle ACB, I would have a statement that says this: the measure of angle ACB plus the measure of angle ACB would equal x degrees, right? Just replacing the measure of angle QBC with the measure of angle ABC, or ACB. And now, if I'm adding two of the measures of angle ACB, I could look at that as saying 2 times the measure of angle ACB is x degrees. And then if I divide both of these sides by 2, the measure of angle ACB will be 1/2 of x degrees. And so you can see the relationship that we were looking to describe, the relationship between the measure of this arc and the measure of this angle, is that the angle here is guaranteed to be half of what the arc is. And so that's kind of an interesting relationship that actually is going to be our first theorem that we're going to talk about in this video. Theorem 10-8 is going to say the measure of an inscribed angle is equal to 1/2 the measure of its intercepted arc. its intercepted arc. So in this picture, if I have my inscribed angle, angle S here, the measure of angle RST will be 1/2 the measure of arc RT. Now remember, the measure of an arc is in degrees. It's describing what portion of the full 360 degrees of the circle does that arc take up. It's not the length of the arc, right? The measure of the arc is not how long it is. It's how many degrees does it take up for the full circle. So that's theorem 10-8. The measure of an inscribed angle is equal to half the measure of its intercepted arc. So in this picture here, this angle here, if this was an x degrees out here, this angle would be half of x degrees. Now, there is a corollary, or corollary, however you want to say that. There is a corollary to this theorem that says two inscribed angles that intercept the same arc. So if what is this talking about? If I look at this picture over here, I would have this blue inscribed angle, angle RSU. It's an inscribed angle because its vertex is on the circle and its sides are chords. It is intercepting this arc. And then this reddish inscribed angle, angle RTU, is also intercepting that arc. So it would probably make sense to you to say, well, those two angles must be the same measure because they're intercepting the same arc. So if this was, say, 80 degrees, right? If this was maybe 80 degrees, these would both be 40 degrees. And no matter what I make this arc measure, since these would both be half of that number, they're always going to be the same. So we're going to finish this corollary by saying two inscribed angles that intercept the same arc are congruent. We can go farther than that if we have an inscribed angle that's inscribed in a semicircle. So what that means is, what this is saying is if its intercepted arc is a semicircle, it's inscribed in a semicircle, then that angle, then the angle's measure will always be 90 degrees. Or we can say it is a right angle. Sometimes you'll see this, this idea written that way. Then an angle inscribed in a semicircle is a right angle. The measure of angle RTS is 90. And finally, one more addition to this idea is that if I have what we call an inscribed quadrilateral, what that is a quadrilateral whose vertices all lie on the same circle. So if I look at this picture, I would be talking about quadrilateral RSTU because you can see all four corners of that quadrilateral are on circle C here. So what would we know about these opposite angles? Well, if you think about, let's just look at two of them. Let's look at angle R and angle T, right? The measure of angle R would be half of arc STU. All right, so I'm going to write that down. I'm going to write that down over here. This is going to kind of be my proof for what's happening over here. The measure of angle R is half of the measure of arc, arc STU. The measure of angle T would be half of arc SRU, half the measure of arc SRU. But if I add together those two arcs, well, actually, let's do it this way. Let's say what would happen if I take the measure of arc STU plus the measure of arc SRU, right? I know that's going to be 360 because together, if you put those together, you now have the full circle, right? So these two arcs together would equal 360. Now, if I take half of both sides, so if I take half of the measure of arc STU plus the measure of arc SRU, that would have to equal 180 degrees, right? Half of these two arcs together would be half of this side, which is 180. And then if I distribute that 1/2 in, half of the measure of arc STU plus half of the measure of arc SRU would have to equal 180 degrees. Now here's the payoff. If I take this and I replace it with the measure of angle R, and I take the half measure arc SRU, right, I see that right up here, and I replace it with measure of angle T, it tells me that angle R and angle T have to add up to 180. And I could have done the same thing with S and U, right? I could have looked at those two angles and I could have looked at their arc measures. And the same thing would have happened is that these two would end up adding up to 180. And so what we can say that's geometrically interesting is that opposite angles, they add up to 180, and we say that means they are supplementary. I've kind of written all over the place where I probably would have preferred to finish that sentence. So let's just say that, they are supplementary. The opposite angles of an inscribed quadrilateral will always be supplementary. And that, again, it's all building off this idea that an inscribed angle's measure will be half the measure of the intercepted arc. Right? And from that we can say that if two inscribed angles intercept the same arc, they have to be congruent. We can say that an angle that's inscribed in a semicircle would have to be a right angle, and we can say that the opposite angles of an inscribed quadrilateral will have to be supplementary. They'll have to add up to 180. One more idea that we're going to talk about is another kind of angle. It's not technically an inscribed angle, but it has something in common with it. We're going to look at this angle right here. Now that angle is being formed by a chord and a tangent line, or a chord and a tangent, right? I see a chord here, segment AE, and we're going to call this a tangent right here. Line DE is tangent. Its point of tangent C is right there at E. Right, so that angle, it's intercepting an arc. It's intercepting arc AE, right? It's kind of, if you look at the arc of the circle that's like inside that angle, it would be this arc, arc ABE or arc AE. The measure of that arc will also tell us something about the measure of the angle, and it's the same relationship we had above. The measure of an angle formed by a chord and tangent is equal to half the measure of its intercepted arc. And so one of the ways I think of this, one of the ways I remember what all this is saying, is I remember that if an angle's vertex is on a circle, on the circle, right? If it's on the circle, its measure, the angle's measure, will be half the measure of the intercepted arc. So no matter if it's an inscribed angle where the vertex is on the circle and the sides are chords, like we might see up here, right? Vertex on the circle and its sides are made of chords, or it's this kind of angle, which doesn't really have a name, but its vertex is on the circle, one side is a chord, but then the other side is part of a tangent. If its vertex is on the circle, its measure is going to be half of the intercepted arc measure. And that's kind of the main idea for this section.